Shen from Peking University, and I'm glad to talk about our work on software merging. And we developed IntelliMerge, a refactoring-aware merging technique, and our work is sponsored by Peking University and Huawei Technologies. Well, what's wrong? Well, by seeing the software merging, we specifically mean the code merging that happens in version control systems like Git, where developers separate their tasks like new feature or bug fix in different branches and merge them frequently. Okay. And there are a variety of merging techniques that are available. We all know that most popular Git merge, it considers the source code as text and merges them line by line. So it's one of the unstructured merging. And for the structured merging, they represent the code in data structures like abstract syntax trees or graph. And for the semi-structured merging, not all of the code are merged structurally, but part of, like the method body, are still merged textually in semi-structured merging. Okay. Oh, I don't know what's wrong. Okay, sorry for that. Maybe it will cause some delay to the lunch. Okay, I will just show like this. Is that okay? Yeah, okay. So as the most widely used merging tool in the industry and academia, the Git merge has several problems. For example, if we have some semantic irrelevant change like reformatting or moving a method inside a class, it could lead to some false positive conflicts, which are not real conflicts. And since the Git merge considers the inconsistent modification to the same line as a conflict, so it can miss some semantic or logic conflict, and thus produce incorrectly merged code. And what's worse is that in case of complex changes like refactoring, it can produce some confusing merge results and conflict blocks, which are very hard for the developers to resolve them. And it drags the behind, okay? So we target at overcoming the limitations of Git merge, especially for refactoring. I believe that everyone knows what refactoring is. For example, refactoring has become increasingly popular in agile development and with the support of automated tools. But they bring trouble to the current merging techniques. For example, the Android phone vendors like Huawei, they usually build their operating systems on top of the Android project of Google. But in order to update their kernel, they need to constantly merge the latest code from Google. And at each merging point, because of the many refactorings and changes applied independently into companies, there could be tens of thousands of conflicts if we use Git merge. And in a recent study on about 3,000 Java open source projects, they found that over 22% of merge conflicts are related with refactorings, and they are more complex and difficult to resolve. So what are the challenges to correctly merge refactorings? In our point of view, we think that refactorings often leads to mismatching in existing approaches, so the matching is the basis of a better merging technique. And secondly, the multiple changes that consists of the refactoring should be merged systematically, but current approaches do not consider the consistency. And secondly, usually the refactoring history is missed is unavailable to the merging tool and the developers. So correct comprehension of the merging of the refactoring history is vital to the merging. So we want to develop a refactoring-aware merging technique, which was first proposed by Danny Dick in 2006. And we want to match the refactored code based on the graph fragmentation of the OOP programs, because we think that matching is the basis of the better merging algorithm. And we expect to produce better merging results and fewer but more reasonable conflicts. Okay. So here I gave you the overview of IntelliMerge, which is a graph-based and refactoring-aware technique. Basically, it works in 4 steps. Step 1, given the 3 versions to be merged, we convert the code into graph through lightweight semantic analysis. The graph is called program element graph. And next, with the graph, we can match the vertices in the graph and merge the matched vertices. And finally, print the merged code with the possible conflict blocks embedded in them. And it's open sourced on GitHub. Okay. So here I will introduce the definition of the program element graph. Basically, it's a labeled, weighted, and directed graph that encodes the program structure and the data flow and the control flow, but above the method and field level, because we are semi-structured way. And we care about maybe only the structural refactorings, so it affects the program structure above the field or method level. Okay, and the vertex set of the program element graph consists of program elements like class declaration or method declaration, and we further categorize them into the terminal and non-terminal ones. And the edge side consists of the relation and the interaction between the program elements like extend and field access. Okay, the implementation of PEG is language specific, just like the other tools in the software engineering. And here we list our supported tabs for Java 8. And next, I will introduce some steps in detail. And for the first step, the input of the first step is 2 branches to be merged. And the output of this phase is 3 graphs corresponding to the left, right, and base version. And given the 2 branches to be merged, we first locate their head commit, which is called left and right commit, corresponding to the branches. And firstly, we need to find their base. It is the nearest common ancestor in the commit tree, which is this point. And secondly, we will compare the left and right version with the base version, respectively, and get the diff files and also their important files. And then we will pass the source code containing these files and pass them into abstract syntax trees, and then extract the program elements from those trees. And for the last step, we are going to analyze the bodies of the terminal vertices and find some the relations between the program elements, thus forming the edge side. Well, during this process, some information are collected, which is necessary for the matching. For the vertex, each vertex has a type, like class or method or field, and each node or each vertex has its signature, which is the qualified name of the program element. Like this one is for a class, which contains its package name and the class name. And for method, in case of the method overloading, we also include the method, the parameter type list of the method declaration. And of course, the corresponding source code of the vertex. And for age, each age has a type like define or call or rate. And it has a weight, which denotes the times that this relationship appears between 2 vertices, like how many times method A invokes method B. And next step, we are going to match the vertices between the left and base, and or right and the base, respectively. And here we employ a 2-phase process. In the top-down phase, we will match the vertices from the top to down. Okay, and In this step, we will filter the vertices with unchanged signature. And in the bottom-up phase, we will match the vertices according to the matching degree. Okay, by seeing the matching degree, we use it to roughly estimate how similar of two vertices across the two graphs. And for terminal nodes like method or field, we take their signature and body tree and context edges into consideration and compute a weighted average of these similarities. And for non-terminal vertices, we replace the body tree with a children list. And when it comes to the refactoring, instead of detecting each refactoring type like move method and rename field, we categorize them into two categories according to their effect or their result. For example, in the one-to-one matching, the renaming, moving, pulling up, or pushing down, they all result in one-to-one matching because if you rename a method, it's still a method in the new version, right? But if you extract method or inline method, it will become many-to-many matching because you can extract several methods from one, and also you can inline multiple methods into one. Okay, so since we assume that the matched program elements must have the same type, because those refactorings won't change its type. So here we employ a divide and conquer to speed up the matching process. Okay. And once the matching is done, we keep the matched vertices in triples. And the output of the merging process is the merged code files with possible conflict blocks. So the merging and the code printing happens simultaneously. And firstly, we will locate all the vertices of type completion unit, since physically the source code is organized as source code files, which corresponds to the completion unit. And secondly, we will traverse the nesting edges starting from the completion unit vertices and merge the children recursively. And during this process, if the left and the right side modifies the same node, but in different ways, there will be a conflict. And here we merge the vertex by components. By saying components, we mean, for example, for a method declaration, we merge the comment, the annotation, the signature, and the body separately, so we can produce fine-grained conflicts. We have also done some experiments to evaluate different merging approaches. We collect 1,070 merge scenarios that contain refactoring-related conflicts. And we compare the three merging techniques, which is our proposed graph-based semi-structured one and the most widely used unstructured one, and also state-of-the-art tree-based. Well, our approach is graph-based, is tree-based. And we evaluate by replaying the merge scenario with the three tools and analyze the result. Well, generally, the merge result contains two parts. Some code are merged without conflict, and some are conflicting and waiting for the developer to resolve. So we evaluate the result in. Okay, I think here we should have some animation. Okay, so we evaluate them separately. And first, for the merged code that has no conflicts, we define the precision and recall to estimate the result. And interactively, the precision estimates how precise the merging tool can merge the code correctly, and the recall estimate the proportion of the correctly merged code in the comparing to the manually committed code. And we use the texture diff to compute the difference, the different lines. And here are the results. On average, our approach achieves about 88% of precision and 90% of recall. But let's look at this column. It's strangely high for gate merge. The reason is that we use the manually committed code as the ground truth, and all the studied projects use gate merge as their default merging tools. So this precision estimates how close the merged code is to the manually committed code. So its high is not strange. And we also manually review some code and found that in some, this is the merge commit, and this is the code that obviously have errors. And even some developers even commit the unresolved conflicts in a merge commit. And we are working on better ground truth to estimate the results. Okay. And we also count the completing code in terms of the number of complete blocks and the length of completing code. Well, from statistics, we can see that both the two semi-structured merging approaches can significantly reduce the number of conflicts comparing to the unstructured gate merge. And for our approach, we can reduce the length of completing code by about 90%, which is very great. And comparing to GFST merge, our approach can further reduce the number of conflicts by about 12%. Well, here we come to the conclusion and future work. We propose an algorithm that can match the refactored code and merge them correctly. And we have implemented a tool, which is a Refactoring-Aware tool for Java and open source. Actually, it has been used in Huawei and to speed up the delivering of the new EMUI 10 system. And what we are doing is to overcome the second and the third challenges that we proposed before. It is we want to make use of the dependencies between the conflict blocks to help the developers to systematically resolve related conflicts. Like if you accept a master renaming in one conflict, then in the master invocation in other conflicts should be accepted correspondingly. And we also want to check the syntactic or semantic consistency between the merged program elements, so we can make sure that the merged code are basically syntactically correct. Okay. So I don't know the time because of the. Okay, so here we come to the questions.
Hi, thanks for your talk. I think this is really interesting. So I can imagine when merging these large code bases like an Android kernel, it might take quite a bit of time to merge two code bases together. Do you have any idea on timing difference between Git merge and IntelliMerge?
Oh, sorry, what's the difference?
So difference in how much time it costs to merge?
Performance, right?
Yes.
Yeah. Oh, well, I did compare it in the paper, but I didn't put it.
Okay.
Okay. So it's basically because gate merge is text-based, it's very fast. It can finish the merge scenario in milliseconds, but our approach can finish on average each merge scenario in about 500 milliseconds, which is half a second, and is acceptable in practical use.
Okay, thank you.
Thank you.
All right, thanks. I was trying to understand better in terms of what the program element graphs look like, in the sense that what they capture, and how would that be different than the tree matching based algorithm, or what's beneficial about the program?
Okay, for the tree-based merging, they treat each component, each program element separately. They for gate merge, they merge the source code file by file and line by line. So their atomic unit is the texture line. And for the tree-based merging, their atomic unit is a tree, which maybe some a method or a field, but they didn't capture the relations between them, and they cannot find the refactorings because they merge the code tree by tree.
Mm-hmm.
They don't capture the relations or the dependencies between them.